So this is a short video dealing with a specific aspect of addition reactions, and it outlines this rule known as Markovnikov's rule that really allows us to predict which one of two products is going to be predominant product. At certain times, an addition reaction will produce two possible products. Remember, addition reaction typically between an unsaturated hydrocarbon and something else. In this case, we're looking at between halogens or other simple inorganic reactants. That could include water, that could include ammonia, something like that. So let's look at the first example. And in this example, I'm just going to bring to light a couple of ways we look at our reactants. So here we have but-2-ene. So but-2-ene double bond between carbon 2 and carbon 3. So but-2-ene, start of the double bond on carbon 2. Now if we look at what comes off the carbons of that double bond, we see a methyl group, so a single carbon there, and another methyl group off carbon 3, a single carbon. So carbon 2 has a single other carbon bonded to it. Carbon 3 has a single other bonded carbon to it. And so we can classify this alkene as symmetrical around the double bond. And so that's an important point to realize. That symmetry is going to sort of affect how the reaction plays out. So that's our organic reactant. But-2-ene is a symmetrical organic reactant. Well, our inorganic reactant in this case is Cl2, and again we realize that Cl2 is a diatomic molecule with a single covalent bond, so that is also a symmetrical reactant. So the inorganic reactant is symmetrical. So just take a second. You should be able to predict the product of this reaction, this addition reaction, based on but-2-ene having its double bond broken and adding chlorine across it. So see if you can even just name it. So if you did name it, you would have named it 2,3-dichlorobutane. So there's the product, 2,3-dichlorobutane. There's only one possible product. One of those chlorines gets attached to one of the carbons, and the other chlorine gets attached to the other carbon of the double bond. There's no other way around that one. So we only get a single possible product here. Well, let's look at this example. So now I have but-1-ene. And so again, let's just quickly look at the symmetry of but-1-ene, and hopefully you'd realize pretty quickly that it's not the same. So here's my carbon 1, carbon 2 of the double bond. And so in carbon 1 I have nothing, no other carbons bonded to it other than the carbon of the double bond. Whereas with carbon 2 I have this carbon, and I have a second carbon, the carbon of the double bond. So that is an asymmetrical alkene. It's not symmetrical around that double bond, and we still have chlorine. And so our chlorine, again, still looks like chlorine with that single covalent bond. So what about the products of this reaction, possible products? Well, once again, there's only one possible product. And once again, the reason is because of symmetry. But even though the alkene is asymmetrical, we still have only two carbons to put these chlorines on. They're carbons 1 and carbon 2 when you put our chlorine on each of them. And so 1,2-dichlorobutane is the only possible product. So in a nutshell, when you talk about symmetry and asymmetry, in an addition reaction, if either the alkene or inorganic reactant is symmetrical, you only get one possible product. ever a single product. So you want to look for that symmetry in either reactant, because if you have some, it makes life a lot easier in terms of predicting the products. I mean, you're not really predicting, you're just writing down the product. Well, let's go to our next example. So this is where things perhaps change a little bit. Well, they do change a bit. So again, but-1-ene, our asymmetrical inorganic or organic reactant, and now we have HCl, and so HCl is asymmetrical. So that's an asymmetrical inorganic reactant, and so we have two asymmetrical reactants. So again, I'm going to give you a minute, just maybe pause the video and come up with product or products for this reaction. So if we look at the possible products, well, in this case, we have two possible products. And so there they are. 2-chlorobutane, and that's where the chlorine from HCl attaches to carbon 2 of but-1-ene, and 1-chlorobutane, and that's where the chlorine of HCl attaches to carbon 1 of the but-1-ene. So in this case, with asymmetrical, both reactants being asymmetrical, we have two possible products. So this brings us to Markovnikov's rule. So this is a rule based on experimental observations made on these simple addition reactions involving hydrogen halides to alkenes. So the prediction was likely that you'd expect a 1-to-1 ratio of both of these products, but the observation didn't match that prediction, and it turned out that there is a single predominant product. That implies stability issues. One of these products is more stable, that's why there's more of it present. Okay, so in our last example, we need to predict which of those two possible products will be the predominant product. And so here's how you make that prediction. In so many words, the rule states that when you have an asymmetrical alkene reacting with a hydrogen halide, that's going to be asymmetrical, or other asymmetrical inorganic compound, it could be water, the halogen or functional group adds to the carbon of the alkene bonded to most carbon atoms. That's the carbon of the alkene. Carbon of the carbon-carbon double bond that is bonded to more carbons gets the functional group substituent. So it would get the chlorine. On the other side of it, you can look at it as the carbon of the carbon-carbon double bond that is bonded to fewer carbons gets the hydrogen. Typically the other atom going on is going to be a hydrogen. So let's go back to our previous example and see if we can make that prediction. So again, remember what Markovnikov's rule said. The carbon that is bonded to more carbons gets the functional group. Well, in but-1-ene, carbon 2 is bonded to 2 carbons. Carbon 1, on the other hand, is bonded to only one other carbon. So according to Markovnikov's rule, the carbon that has more is bonded to more carbons gets the functional group. That means it gets the chlorine. So there is our predominant product. Two-chlorobutane. So 2-chlorobutane would be predicted as a predominant product, and it is indeed the predominant product because C2 is the carbon of that bond that is bonded to more carbons. So, one last thing about Markovnikov's rule. The symmetry we're looking at is really the symmetry off the carbon-carbon double bond, and that's what I explained at the beginning. It's the number of carbons bonded to the carbons of the double bond. So this final example hopefully clarifies again a little bit about what happens with Markovnikov's rule. If we look at this organic reactant, what's it called? Well, it's 3 carbons, and there's a double bond occurring from carbon 2 to carbon 3, so this would be known as pent-2-ene. So in terms of symmetry around that double bond, it looks asymmetrical, but how many carbons bonded to the carbon of the double bond? There's still actually only one. So we're going to get two products here because of our HCl, but which one predominates? And so there are possible products. So what we end up with is 2-chloropentane or 3-chloropentane. And so if we try to invoke Markovnikov's rule, the carbon of the double bond that is bonded to more carbons, well, carbon 2 is bonded to 2 carbons, and carbon 3 is bonded to 2 carbons as well. So which one is bonded to more carbons? Neither. So which product predominates? Neither. And so this is where you'd see pretty much a 1-to-1 ratio of those two products. So even when you have something that kind of looks asymmetrical, think about the symmetry off the carbons. It's the carbons of the double bond and how many other carbons they're bonded to that give rise to this symmetry or asymmetry. And so that concludes Markovnikov's rule. Actually, I don't think it does. I think I got one more example here. Yeah. So here's a fairly typical question involving Markovnikov's rule. A reaction between hydrogen iodide and propene. Draw the condensed structural diagram for propene and both organic products. Circle and name the predominant product of this reaction. So it starts with the reactants. Hydrogen iodide, well, that's pretty straightforward, and notice it's asymmetrical. Propene, so that's a 3-carbon alkene, and on carbon 1 we can put our double bond, going to carbon 2, and so there are our two organic or inorganic and organic reactant for an addition reaction. And so it's definitely two asymmetrical reactants. And so what do we get? Well, we get H2Ci, and so we put the iodine on carbon 1 and the hydrogen on carbon 2, or we get the iodine on carbon 2. And so according to Markovnikov's rule, one of these reactants or products is going to predominate, and carbon 2 is bonded to 2 other carbons, and so carbon 2 is going to get the functional group. So that is our predominant product with the iodine on carbon 2, and that is called 2-iodopropane. And so 2-iodopropane predominates in this reaction. And that concludes this video.